All right, so our colloquium speaker today is Professor Özlem Ejder from Koç University. Professor Ejder obtained her PhD from the University of Southern California, and she specializes in number theory and arithmetic geometry. Before Koç University, Professor Ejder had positions at Colorado State and Boğaziçi. She is a recipient of the Marie Sklodowska-Curie Grant and the Baguette Award. Today, Professor Ejder will talk about rational points on curves. The floor is yours.
Thank you. And thank you for the invitation. Okay, so I'll speak about rational points on curves, and I'll try to keep the talk very simple. Okay, so if anything gets complicated, you can just warn me. I'll fix that. Okay, so I'll start my talk with a simple question that you may have seen before. So let me write that. So can we find all right triangles with integer edges? Okay, so geometrically I'm asking, okay, I have a triangle and I have the side lengths A, B, and C, and I want A, B, and C to be integers. And then, of course, if it is on a triangle, then they have to satisfy that A squared plus B squared equals C squared. Okay, so we already know some examples of these, right? 3, 4, 5, or I think 7, 24, and 25, and so on. And you can probably produce many examples, but the question is that can we actually just describe them all? Can we give a solution set that is complete? Okay, and the answer is yes, we can. And let me just ask this question in the following way. So instead of looking at this equation, since C here is an edge length of a triangle, it's non-zero, so I can actually divide it by C. And so I can look at the following equation instead. A over C squared plus B over C squared equals 1. Okay. Now, this should remind you the circle equation, circle with radius 1. So then this says that, okay, I'm actually looking at the points on a circle with radius 1. And so let me draw a circle. So I have my circle, and I'm going to fix one point here, that is -1 and 0. And then what I'm going to do is I'm going to draw a line that passes through this point -1. And as you see in this picture, this point will intersect the circle at another point. So the idea is that if I draw this line L with a rational slope, then this intersection will also give me a solution to this equation where the coordinates are in rational numbers. Okay. So take this L to be a rational slope. Then this will give you a point here, xy, on the circle with both coordinates are in Q. And in fact, this is a characterization of all the solutions. So for each line passing through this point, -1, 0, with a rational slope, okay, I'll get a point. This point will just be given by the second intersection of the line and the circle. So I'll just have like more lines here. Right. And if I make sure that the lines have rational slope, then these points are all going to be points that I want. So I point UV on the circle with U and V are in Q. So in general, when I look at an equation, so in this case, it's a circle equation that's given by x squared plus y squared equals 1. So this equation has two unknowns, x and y, and the coefficients of the polynomial defining this equation are in Q, so they're rational. And since I'm looking at the solutions with coordinates in Q, I'm going to call them rational solutions. Okay. So in general, I'm trying to solve an equation defined over the rational numbers, and I'm trying to find solutions that are also defined in Q. Okay. So that this actually just this process of drawing lines just gives you a characterization of all solutions to this problem. Okay. So this way you can actually just find them all. And in particular, this just gives you a parametrization. And that there are infinitely many. For each slope in Q, you're going to get a different solution. Okay. So let's just try this idea on a different question. So this is my second question, and it says the following. Are there any consecutive integers whose product is square of an integer? Okay, so here maybe I'll wait 30 seconds to see if anyone can come up with an answer. So here we're looking at three, are there any three consecutive integers? Sorry, this is missing. I'm looking for three consecutive integers, which means that I have an integer a, and then another one afterwards, and then another one before that. A minus 1, a, and a plus 1, and I multiply them. And then I want this to be square of some other integer. It doesn't have to be a, it is just some other integer b, and I get the square of that, and I multiply all these numbers. Okay, so then we're trying to solve this. So find rational solutions to this equation. Okay. And so one solution that you can come up with is a equals 1 will give you b equals 0. And similarly, if a equals 0, you will also get b equals 0. And you will also get a equals -1 and b equals 0. And in fact, these will be the only solutions. And I'm not claiming that it's easy to see that these are the only solutions. The only easy part here is to see that these are solutions to the equation that I gave you. Okay, so again, we had this polynomial equation, right? And we were just looking for a and b satisfying this equation such that they are integers. Okay. Now, in this problem, right, again, I have an equation defined by some polynomials. I could also think of it as the following. So I turn this into the equation. So this says that AB is a solution to the equation, okay, y squared equals x cubed minus x. Okay, so if you think of this, okay, if you as a curve, or if you look at the graph of this over the real numbers, okay, then you get something like this over the real number. You have a circle here. So you get a curve like this, and you can also think of this AB as a point on this curve, okay? And so then these points that I listed here are, there's one here, there's one here, and there is one here. Okay, so you got 3 points. And those are the only solutions, only integer solutions. Obviously, there are other points on this curve, but those coordinates won't be given by integers for both A and B. Okay. Okay, so then what's the idea behind these two problems? I had in both a polynomial equation, and then I was defined over Q, and I was looking at rational solutions to these. And so then, and I did the same thing. So then we can just sort of give a general picture. So I'll just denote this as one side is algebra, and the other side is geometry. On the algebra side, we have a polynomial in 2 variables, f of x, y, and then this is defined over Q, over the rationals. Okay, and then you're looking at the solutions, so rational solutions of f of x, y equals 0. Okay. On the other hand, you could do the same thing, but instead of just thinking of this as solving some polynomial equation, you're looking at some geometric shape, like a curve, and then you're looking at the points on that. So then here, I'm going to think of this as I have a curve C defined by this equation. Okay. So this just means I'm looking at the vanishing set of this polynomial or the 0 set of this polynomial. Okay. So in the first example, this curve was a circle. In the second one, it's this one. This has a name that will come up later. I won't say it now. Okay. Now the main question, okay, that we can ask is, if I give you a curve C, then can we find the rational points on it? Or at least what can we say about it? Okay. So maybe one thing about the notation that I'm going to use later, so I should just say it now. So I'm going to be working with just curves defined over rational numbers. Okay, this just means that this polynomial f has coefficients in Q. Okay. So we can fix that. And I'm going to just write this as whenever I have a curve C that is defined over Q, I'll just write C over Q like this. So it just means that I'm working over an equation with rational coefficients, and I'm mostly interested in finding rational solutions or rational points on this curve. Okay, so now let me state the question that we're going to be interested in. So given a curve C, defined over Q, what do we know about the rational points? What can we say? Okay, so in general, we write this set as C of Q. Okay. And this just means that I'm looking at the points A, B, such that if C is defined by such a polynomial, I'm looking at f of A, B equals 0. Okay. And I want this A and B to be defined over Q. So this is Q cross Q. Okay. So A and B are both in Q. And so, okay. So in general, if you give me an arbitrary curve, it's not so easy to compute the rational points on it. Okay. And for some curves, it is easy, but it's not guaranteed that we can always solve it. But there is one important thing that we know about the set, its cardinality, okay? Looking at the curve, we can easily tell if there's going to be finitely many or infinitely many rational points on it. So this is a theorem of Faltings. I think from 83. And it was a conjecture of Mordell from 22, I think. Yes. And the theorem says the following. So let C over Q, okay, be an algebraic curve. And I'm going to say curve of genus G, and I'll describe what this genus is in a bit. Okay. Then it says the following. If this genus is 0, then the set C of Q, so set of rational points, is either empty, okay, or it's infinite. So this says that if you can find one rational point on it, then you can actually produce infinitely many, okay, and you can parametrize them. And the second one is that if the genus is 1, then C of Q can be both finite or infinite, depending on the curve. So genus does not necessarily say that it will be finite or infinite in this case. And the third case is that if the genus is greater than 1, then C of Q is always finite. It can also be empty, of course. Okay, so now what is this genus? Okay. So this genus is an invariant of this this curve. Maybe there are two ways of going about this. So let me do the following. So we have this. You don't have to know the words that I'm going to say now. It's okay if you never heard about them. So we have one set on one side. These are the Riemann surfaces. Okay, so these are complex manifolds of dimension 1. And they should be connected. Okay. And then on the other side, we have curves. But I'm going to write here as algebraic curves, but these are the ones that I've been looking at in this talk. So this just means I'm looking at the curves defined by polynomial equations. So these algebraic curves are also defined over C. Okay. So on one side, we have topology, and here we have the arithmetic. And so we talked about this invariant genus, okay, G. So here on this side, I could define it as, so if you have a curve C, say, defined by some polynomial equation, f of x, y equals 0, then if you just take the degree of this polynomial f, okay, then you can define the genus as d times d minus 1 over 2. But you just have to make sure that this polynomial, okay, defines a smooth curve, which just means that you have to look at the partial derivatives that at every point, and you have to make sure that they don't both vanish. Or in other words, you can also think of it as you have some curve, and at every point you want a tangent line. Okay. And so then you can easily describe this algebraically in this form. Okay, that's your genus. And on this side, you can think of this as these Riemann surfaces, or the complex manifolds of dimension 1, as these shapes. So genus 0 corresponds to, so I'm going to just write down the compact ones. So then this is the sphere. Genus 0, or you can have a torus, okay, with one hole, genus 1, And then you can think of it as just arbitrary genus as you have the number of halls equal to G. Okay.
So I have a simple question here. You're drawing what seems to be two-dimensional things, but you're calling them one-dimensional. Like, what is the reason behind that? Why do you call them one-dimensional?
So one-dimensional over the complex numbers.
Okay.
So we say a surface, you're thinking of it as like in R2. But as a curve, it's over C, so it's just one-dimensional. That's why. Okay, so then the genus is, you can think of it as like either just with this easy genus degree formula, that's something that you can calculate, or topologically, it just corresponds to sort of the number of halls in this shape. Okay. And so then this theorem basically says that if you have the genus is greater than 1, it's always going to be finite. So then, and this one is that it's, if you have 1 point on it, then it's going to be infinite. So the interesting case then remains to be number 2. When is it finite? When is it infinite? And what kind of structures do we have on it? Okay, so maybe going back to the examples, we can say something here. So the first example that I gave you, right, looking at the points on this circle, so this corresponds to the genus 0 case. So question 1. And the second one is coming to a genus 1 case. Okay. So for instance, here, instead of looking at this equation, x squared plus y squared equals 1, if you looked at x squared plus y squared equals -1, then you wouldn't be able to find any rational solutions. And in that case, it would be empty set, okay, instead of just being infinite. All right, so then the genus 1 case, what do we know about this? Okay, so in the genus 1 case, let me just give you the definition first. This is what we call the elliptic curves case. So if you have a smooth curve, I'll give you a more explicit definition, but this is the usual definition that you will see everywhere. A smooth projective curve of genus 1. With a specified point. So you choose a point on it. Okay. It's called an elliptic curve. And there's an easy description of such curves. Okay. So if you have such a curve and such a point, you can always just put it in the following form. So the elliptic curves, I'm going to write them not by C, but instead by E. And then you can always just put them in the following form. They're given by the zero set of y squared equals f of x, where we have some conditions on f. One is the degree of f is 3. So this is a cubic polynomial. And that f has no repeated roots. Okay. So first one, the degree of f equals 3. Okay, so this just means that y squared equals x cubed plus blah, 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 something, okay? And the second condition here says that f has no repeated roots. This just makes sure that your curve is smooth, which means that at every point you will have a tangent line that is well defined, okay? So if this condition is satisfied, then you get a smooth curve, and then just looking at the degree of this polynomial 3, you can calculate the genus, you will find that genus is 1. Okay, So then let me just give you some examples.
So what is the specified point here?
So you choose a point on the curve to put it in this form. This is called the Weierstrass form. Okay, so in general, this could be given by any degree-free polynomial in two variables, x and y. Okay, so for instance, take the Fermat's cubic, x cubed plus y cubed equals 1, or that equals z cubed if you want. Okay, so this is not in this form, but if you just fix a point on this, okay, a p, so that's like, I don't know, 1, 0, 1, for instance. Sorry, 1 and 0. Then using this point and just doing some manipulations that are allowed, whatever that means, then you can put this into this form. Okay. This is called the Weierstrass form. Okay. All right. Okay, so then I'm going to say that this E is defined over Q if this polynomial f of x is defined over Q. Okay, which means my equation again has coefficients in rational numbers. Thank you. All right, so then what do we do with this? Okay, so I was gonna give you some examples. One is the example that we actually looked at before. This came out of second question. Y squared equals x cubed minus x. Okay, so this is an elliptic curve. And the second one, you could just say y squared equals x cubed plus 1 or x cubed plus x plus 1. Okay, you can just produce many examples. You just have to obey this rule. And non-examples are y squared equals x cubed. Okay, so this is not okay. This is not an elliptic curve. And the problem here is if you look at the graph of this, okay, at 0, 0, you will have this sharp turn. Okay, so you have a singularity here, and this corresponds to having this repeated root, right? X cubed has a root 0 that is repeated 3 times. Okay. And you can also have y squared equals x cubed minus x squared. Okay. Again, I have the repeated root 0, this time repeated 2 times. Okay. And this curve will intersect itself. And so this is not allowed either. Okay. Okay, so then I'm just looking at these non-singular curves. Okay, so what's special about these is I'm going to try one thing. So in the first example here, right, we just parameterize the solutions to this equation by just drawing some lines. Okay, so I'm going to try the same thing to see if that helps. So let's say I have an elliptic curve. Actually, it doesn't have to be defined over Q. Let's just say it's over C. And maybe better Q right now, so we don't get in trouble. Okay, so then we have some sort of graph, right? This is a cubic polynomial, and it will just give you a graph like this. So this is a graph, of course, in R2. Okay. And so here, what I'm going to do is, right, let's say that I have a point P in here, and I draw a line, okay, an arbitrary line. And I see that this line, not like before, right, intersects the curve at 2 other points. Okay, and this is basically because we have a degree-3 equation, and so it's a degree-3 polynomial. You expect to get 3 solutions when you intersect a line. Okay, so you're solving a degree 1 equation and a degree 3 equation, and you just expect to get 3 solutions. And as you see in this picture, you get them. So this means that, okay, this doesn't quite work, but maybe what I can do is the following. Say I pick actually 2 points on this curve, P and Q, okay? And then I draw a line, L. L is a line passing through P and Q. Okay. Then I expect this line to intersect this curve at a 3rd point, okay? And then what I see, actually observe here, that there's a group law. Okay. if you like. So you can just do this actually over any field. I'll just write here E of Q, okay? And that says the following, that if 3 points on this curve lie on a single line, then their sum is 0, okay? So this is your, this just means that you turn the set into a group, okay? So there is just more structure than just an arbitrary set. So this is your identity element, okay? So there are some hidden things, of course, here. So one thing is, okay, what is the 0? Where does that live in this picture? Okay, so the nice thing about this equation here is this y squared equals f of x. So this is the picture that we draw in the affine space, the usual, right, xy coordinates. But we actually think of this elliptic curve in the projective space. Okay, so I won't get into the details of this much, but in the projective space, what it does is it adds points at infinity. And on this elliptic curve, there is just one point that you don't see. Okay, so there's one extra point here, that's O, and that's not given by any of these xy coordinates. Okay, so that's an extra point up here, and then you have the usual plane down here. Okay, and what happens is with this point is any vertical line that you draw, okay, that any vertical line that you draw will pass through this point O. Okay? And so then this says that for any point on this curve Q, this point here will be the inverse of that. Okay. So this, let's say that Q is given by A comma B, and then this point here is A negative B, and this is the inverse, the additive inverse of Q. Okay. So what's hidden in this picture is that we work in the projective space. Okay. And that there is a point at infinity. And every vertical line passes through this point. Okay.
Can I
So
ask something?
Yes, of course.
Do we define the inverse like this, or do we find the inverse to be a comma minus b?
So what we do is we define the addition of P and Q. So I start with these 2 points, P and Q. I define the addition, P plus Q, as this point. So not R. Okay, so here. So I have P and Q that I start with. Okay. And then I look at the third intersection of this line, and then I draw a vertical line, and then just get the intersection. Okay. So this one is just P plus Q. So when you define this, okay, then afterwards you find your identity element and also the inverse. Okay. So with this definition, the identity element is the point at infinity. Okay. So over here somewhere. And then the inverse, so if it is that, then as you can see, right, on any vertical line, you have the identity, and then you have this point R, and then you have the other one where you take the symmetry of the y coordinate, okay, with respect to the x-axis. So then these 3 points, when you add them up, you get 0, but this is already 0, so this is your identity element here. Okay, so that means R and this point are inverses of each other.
Okay, thank you.
So in other words, I guess you can say that we define this addition so that this extra point that we add at infinity becomes your identity element. Okay. But you can think of the motivation just coming from the first problem, the parameterization of points on the circle. Okay. So what do we know about this group? Right. So if you see a group, the question that you ask, what kind of group is this? Okay. And as I change my elliptic curve, how can this group change? Okay. So those are the questions that we ask. And so this is a theorem of Mordell. that if you take an elliptic curve E over Q, okay, then if you look at the set E of Q, so this is all points with rational coordinates on this curve E, this is a finitely generated abelian group. Okay. So I just mentioned that there is a group structure on this, and this abelianness just comes from the definition. So the theorem here is really that this group is finitely generated. Okay, so it means that there is a finite set of points where you can just add them, okay, and get every other point on this curve. So in particular, this can be infinite, but there is at least a finite set of generators, okay, where you just have to compute, and then you can get the rest of the points using those. And we have a classification, right, of finitely generated abelian groups. We have a theorem that says the following. So if it's finitely generated, then E of Q looks like this. So you have a bunch of copies of Z. So this is the infinite part. Okay? And plus you have some finite group here. Okay. You can also just describe this finite group nicely, but it doesn't matter for this talk. Okay. So this R here is called the rank of this curve E. There's a lot of research going on this R, and this finite group is called the torsion subgroup. So say this is a group, right? You can have elements of finite order or infinite order. So if you have an element of finite order, it lives on this part, okay, in this torsion subgroup. So this is the set or the group of points of finite order. They're all in here. Okay, so then maybe I'll just mention a few things that we know about this R and the torsion. Okay, so first about the torsion, this is a theorem of Mazur from 77. Okay, and it says that if you have again a curve, elliptic curve over Q, then E of Q has a point of order n. So this is just fixing an elliptic curve E, okay? And you assume that you have a point of order n, not just an arbitrary point, a rational point, okay? If and only if this n is one of the following. So it's either one of the integers from 1 up to 10 or 12. Okay, so it has to be one of these. And yes, you're skipping 11 here, not here. Okay, so this is the theorem of Mazur, and I think it was conjectured by Og, okay, a while ago. I think it was actually a long time ago. I don't remember now the date, but it was conjectured by Og and then proved by Mazur in 1977. So after this, we also have like versions of this theorem for degree 2 fields, degree 3 fields, and so on, but I won't get in there for now. So maybe one thing about this rank R. So there's some, let me just mention a few interesting things. So Elkies found this elliptic curve E. So this is from last year, 2024. That there is an elliptic curve, an explicitly given elliptic curve E defined over Q with rank at least 29. Okay. It is conjectured to be 29, I think, but we know that it's at least 29, it could be more. Okay, so one question that, of course, people ask is that, okay, if I just change my curve E, right? So I can write many elliptic curves defined over Q with coefficients in Q. How does this rank change? Okay, so is it bounded or unbounded? Okay, so there is a result of Elkies again. Okay, and again, I don't know the date. It says the following, that there are infinitely many elliptic curves over Q of rank 19. Okay, so these are just like some random integers that show up. But then there are some heuristics, no theorem, okay, nothing proven. There are some heuristics that says that there are only finitely many elliptic curves of rank greater or equal to 21. Okay, I think so some people are also trying to show that as the curve E varies, this rank is bounded. Okay, but there is really not much progress there.
So when you say heuristics, does that mean that this is known or this like expected?
This is expected.
Okay.
Yeah, so there's a paper, but like no real theorem showing that there are actually finitely many of them. So this is saying that what they find shows that this is expected. Okay, so it's I started. Let me see. Let's get this. Okay, so I want to say maybe one thing, like one actual conjecture I want to state, and then I'll finish it. So since this is talk in number theory, I have to say the word Galois, and so I'll say something about the Galois group. Okay, that connects with this. So let's just go back to Galois. Okay. So I don't know who has taken a course in Galois theory, okay, but let me just sort of try to describe what this is about. So Galois was trying to understand the solvability of polynomials just in one variables. Okay, so if you look at a quadratic polynomial and then you're looking at the solutions, we have this nice quadratic formula that solves it, right? And so in fact, for degree 3 and degree 4, we also have a solution. Okay. So a formula that solves the equation, but that formula is not as simple as in the V2. So we don't usually know it by memory. I don't know it. Okay. But this all involves just like getting some discriminant and calculating it. Okay. And so then the Galois was wondering if this was always possible. So if I just give you some random degree D polynomial, okay, in just one variable, can I solve it? So the way that he approached to this is sort of looking at the symmetries of the roots of such polynomials. Okay, and so from that, actually the whole group theory was born. And so maybe I'll try to just sort of give a vague description of what this Galois group is, and then I'll state the conjecture. Okay, so I'm starting with rational numbers. Okay, and so what I can do is if I just take some polynomial f, okay, and then I'm going to add the roots of that polynomial to the rationals. So for instance, I can add q to square root of 2. Okay, so this just means I'm looking at all complex numbers in this form, a plus b times square root of 2, where a and b are in q. Okay, so I put this extra element square root of 2, and then I extended this so that it still has this nice properties that I can still add things. It's closed under addition, closed under multiplication, and so on. So this is still a field, okay? But I can also do this for anything, really. So I could just do this for q of, I don't know, a cubic root of 2, or a fourth root of 5, and so on, right? I could just write down many examples to this. So what I'm going to write down here is Qbar, which is the algebraic closure of Q. Okay, I'll describe what it is. Algebraic closure of Q just means union of all such extensions that I can create. Okay, so this just means I'm taking, okay, Q of all elements alpha, where alpha is a root of some polynomial defined over Q. Okay, so in this case, this is just a single variable polynomial, degree 3, degree 5, degree 7, whatever it is. I take all the roots, okay? They all live in the complex numbers, right? The roots, I know that complex numbers are algebraically closed, so every polynomial has a root there. So I take all of them, okay? And then I get this huge set, okay? So this is called the algebraic closure. Now, since the elements of the set, okay, or this field, are all roots of some polynomial that is defined over Q, I can look at the symmetries of this. Okay, so what I'm going to call the Galois group, this is called the absolute Galois group of Qbar over Q. Okay, so this is the group of symmetries. Okay, I'll just say of Qbar. Okay, fixing Q. So this just means the following. So if you take, for instance, okay, examples. So if it is just a symmetries of Qbar, that means if you give me an element in Qbar, it should just produce another element in Qbar. And how does this work? Basically, what it does is, okay, so if you have some alpha in here, okay, so that f of alpha is 0 for some polynomial f. Then what this does is, okay, if you take an element of this Galois group, okay, the sigma just takes this element to another root of this polynomial. Okay, so if you have a polynomial defined over Q, what the sigma is, even though it is looking at a huge set, okay, I'm adding all the roots of all polynomials that I can think of. This is still, if you just work with one single polynomial, that you're taking a root, and you know that there's at most d many roots, and so that root has to go to one of those. Okay, so these are the symmetries that we're looking at. And so then in particular, this Galois group here, okay, will act on anything defined sort of algebraically. Okay, so then what I'm going to do is I'm going to take an elliptic curve E. Okay, so let E be an elliptic curve E defined over Q. So this is just defined given by some polynomial with coefficients in Q. And then what we do is we look at, so let's take a prime P. Okay, and I look at this set E of P. And this is the set of, okay, all points on E with order dividing P. Okay, so it's either order P or just one, which is identity element. Okay, and one thing that I know is that this is isomorphic to the following group, Z mod PZ cross Z mod PZ. Okay, so I have P square elements, and this is the group structure. And so what happens here is that the Galois group G, okay, so let me see, Galois group. So this Galois group of Qbar over Q acts on this set. So which means that I have a homomorphism from this group into the automorphism group of EP. Since this is isomorphic to this group, right, then the automorphism group just corresponds to actually the matrices, invertible 2 by 2 matrices with coefficients modulo P. Okay, so my coefficients are not integers, but integers modulo P, and they're 2 by 2 and they're invertible. Okay? And so then what the theorem of Serre says is the following. Okay, so there's a technical term here that I won't describe. So I have an elliptic curve E, okay, that is non-CM. I won't get in there now unless you ask. And this is a curve defined over Q. Okay, again, I have a prime P. Then it says that there is a constant C. greater than 0 such that this representation, I'm going to call that rho EP. Okay. Such that rho EP is surjective for all P greater than C. Okay, so this is a theorem, still not a conjecture, right? There's one problem here. This constant C depends on the curve E. At least in the proof. Okay, now the conjecture. So this is called the Serre's uniformity conjecture. Okay, it says that there is a constant C that does not depend on the curve that you work with. Okay. And I'll just say that this constant is conjectured to be 37. Okay, so it's a very small number. I think I've talked enough. I'll stop here. Thank you.
Great. Thank you for the great talk.